Okay, so we have sledding hill and the flat part. We start at the top, we had motion sensor data. At the bottom, we had motion sensor data, and we measured the distance in between. So we have a distance, we probably have a time for that as well. And I believe we measured, at least somebody measured the angle of the hill. So how do we get the height of the hill? If we're going to look at the conservation of energy part, there's obviously potential up top and some kinetic down below, but we're going to need the height. So we need this distance. Well, we have the length of the hill, the distance labeled D here, and the angle. And if we look at the angle, we do a little bit of trig, and it's, let's see, we want the opposite side, and we have the hypotenuse of that triangle. So opposite side is h, the hypotenuse is the displacement along the hill. If we're looking at opposite side, we're looking at sine of that angle theta. Okay, so that's going to give us the height, which will give us the potential energy. And since we're using real life numbers, using 9.8 is probably a good idea because it's real life numbers, and then we can get the kinetic at the bottom. If we look at the difference between those, the kinetic energy minus the potential energy you get, that should be some kind of change in energy, and work causes that change in energy. What caused the work? Friction along the distance of the hill. We can calculate this. We measured this. Solve for the friction. So that is conservation of energy piece. You know what? I think I'll do this in a couple different videos. See you in the next one.